Hello friends, my name is Vikas, BSc second year chemistry honors fourth semester. Today we will do acid and base chapter. So our first topic is Arrhenius concept of acid and bases. Arrhenius, a Swedish chemist, was the first to define acid and bases in aqueous solution. According to Arrhenius, an acid is defined as a substance which contains hydrogen and which, when dissolved in water, gives hydrogen ions. Accordingly, all mineral acids like HCl, HNO3, and H2SO4 containing hydrogen, when dissolved in a water, dissociate completely into hydrogen ions. Arrhenius named these acids which dissociate complete in water as strong acids. There are other acids like acetic acid, carbonic acids, and phosphoric acids, which when dissolved in water do not dissociate completely into ions. As a result, an equilibrium is between the ions and the undissociated acids molecules as shown below. Arrhenius named these acids as weak acid. According to Arrhenius, a base is a substance which contains hydroxyl group and which, when dissolved in water, gives hydroxyl ions. Thus, substances like NaOH and KOH, which when dissolved in water dissociate completely to give hydrogen ions. Arrhenius named these bases which dissociate completely in water as strong base. There are substances which do not completely dissociate into hydroxides ion, and Arrhenius named these substances as weak base. For example, substances like NH4OH, MgOH2, AlOH3 do not dissociate completely to give OH ions and can written as hydrogen ions obtained from the acids and hydroxyl ions obtained from the base combine to form unionized water. Arrhenius describes these combination of H plus and OH minus ions as neutralization. Arrhenius concept is very simple to apply and explain a number of phenomena like neutralization, hydrolysis of salts, strength of acids and bases. However, there are certain limitations which are described below. First limitation is Arrhenius concept of acids and bases is applicable only in aqueous solution. These concepts fails to explain the acid or basis behavior of substance in non-aqueous medium such as liquid ammonia, liquid sulfur dioxide, alcohol, etc. Second limitation is Arrhenius concept fails to explain the acid character of substance like CO2, SO2 and SO3, etc. and basic character of substance like NH3, Na2CO3, CaO, etc. Third limitation is Arrhenius concept also fails to explain the reactions between an acid and a base in the absence of water. For example, NH3 plus HCl goes to NH4Cl. Although Arrhenius concept of acid and base suffers from a number of limitations, yet the concept is useful and informative for an elementary approach. So our second topic is Bronsted-Lowry concept. Arrhenius concept of acids and bases was further improved by Bronsted and Lowry. Both Bronsted and Lowry in 1923 incidentally introduced the same definition for acids and base. According to Bronsted-Lowry concept, an acid is a substance which can donate a proton, whereas a base is a substance which can accept a proton. In other words, an acid is a proton donor, whereas a base is a proton acceptor. As a result, Lowry-Bronsted concept is sometimes called the proton donor acceptor concept. It can be represented as acid is in equilibrium H plus base. According to Bronsted-Lowry, a neutralization reaction involves to realize of a proton by an acid for the acceptance of that proton by a base. For example, the reaction between HCl and NH3 to form the ammonium chloride can be represented as The curved arrows show how electron must arrange to result in the transfer of hydrogen atom from the acid to a base. The unsaid pair of electrons on the nitrogen of ammonia is attracted by the partial positive charge on the hydrogen in the polar hydrogen chloride molecule. A comparison of the structure of the reactants and the products so that the hydrogen atom which was bonded to chlorine in a reactant, it is a Bronsted-Lowry base. A species must have at least one unsaid pair of valence electrons so that it can form a covalent bond to the proton to act as a Bronsted-Lowry acid. A species must contain at least one hydrogen atom that is attached to an atom that is more electronegative than hydrogen. In case of HCl loses a proton is an acid. Ammonia accepts a proton from HCl and is a base. It is important to note in the above examples that water acts as a base and respect to hydrochloric acid and sulfuric acid. Intrinsically, water acts as an acid with respect to ammonia. Such a substance which acts both an acid as well as base is called amphoteric nature, or similarly bicarbonate ion behave as a acid and a base. Other example of amphoteric substance is hydrogen sulfate ion. HCl being an acid donates a proton and form Cl ion, whereas ammonia being a base accept a proton and form ammonia ion. Now the chloride ion has a tendency to accept the proton, whereas ammonia ion has a tendency to donate a proton. In other words, an acid donates a proton and become a base, and a base accept a proton and become an acid. Thus, a base formed from an acid is regarded as the conjugate base of acid. Similarly, the acid formed from a base is called the conjugate acid of the base. In the example above, between HCl and NH3Cl is the conjugate base of HCl, and NH4 plus is the conjugate acid of the base NH3. Acids and base that are related by the losses or gain of H plus ion are called conjugate acid base pairs. It is clear to indicate that any acid and base reaction would involve two acids and two bases. These acids and bases are called conjugate pairs. In the above example, HCl is an acid since it donates a proton, and Cl is its conjugate base. Water accepts the proton and hence is a base. Thus H3O plus ion is the conjugate acid. A strong acid has a weak conjugate base and vice versa. It is further important to note the Bronsted-Lowry concept is not restricted to only neutral molecules. The concept is equally applicable to ions as well. A careful inspection of the above discussion reveals that first is a substance is capable to showing acid character only if the other substance is capable of accepting the proton, that is a base. For example, HCl is an acid in aqueous medium because water can accept the proton from HCl. However, HCl is not an acid in benzene because benzene does not accept H plus ion from HCl. Second is not only neutral molecules but cations and anions may act as an acid or base. Third is both Arrhenius and Bronsted-Lowry concept require an acid to be source of proton. Thus, all Arrhenius acids are Lowry Bronsted acids. Fourth is according to Arrhenius, a base is a substance which gives OH minus ions in solution, whereas according to Bronsted-Lowry, a base is a substance which can accept a proton. For example, CO3 2 minus plus H plus goes to HCO3. Bicarbonate ion is formed. Carbonate ion CO3 2 minus cannot give OH minus ions in aqueous solution. It therefore cannot be an Arrhenius base. Thus, all Bronsted-Lowry bases are not Arrhenius bases. Limitations of Bronsted-Lowry concepts. Although Bronsted-Lowry concept could explain the shortcomings of Arrhenius concept, yet it could not answer some of the well-established reactions. For example, it cannot explain the reaction between the acid oxides like CO2, SO2 and SO3 plus with the base oxides like CaO and BaO and MgO, which take place even in the absence of water. For example, CaO plus SO3 goes to CaSO4. Clearly, in the reaction between CaO and SO3, there is no proton transfer involved in the reaction. The acid nature of compounds like BF3, FeCl3, AlCl3. Next topic is Lewis concept of acids and base. An acid is a substance which can accept a pair of electrons. A base is a substance which can donate a pair of electrons. In other words, an acid is an electron acceptor. It means that a substance which has vacant orbitals to accommodate one or more pair of electrons can act as a Lewis acid. On the other hand, a base is an electron pair donor. It means that any substance with unsaid pair of electron can behave as a Lewis base. Thus, the acid base or neutralization reaction involves the formation of coordinate bond between the electron pair donor and the electron pair acceptor. For example, the reaction between the boron trifluoride BF3 and ammonia NH3 is a typical Lewis acid base reaction. Let us now discuss in detail Lewis acid. According to this concept, Lewis acid are classified as first statement is molecules having central atom with an incomplete octet of electron. Boron trichloride, boron fluoride, aluminum trifluoride, etc. are acids of this type. It is clear that the central boron and aluminum atom have only 6 electrons. Second statement is simple cations. All the cations are short of electrons and can behave as a Lewis acid. Large sized cations like Na plus, K plus, Ca2 plus and Ba2 plus etc. behave as weak Lewis acid. This is because these have little tendency to accept electrons. On the other hand, small sized cations such as H plus, Ag plus, Li plus ions have a strong tendency to accept the pair of electron and are strong Lewis acids. In addition, highly charged cations have a higher tendency to accept the electrons pairs relative to lower charged cations of the given metal. For example, SN4 plus is a stronger Lewis acid than SN2 plus. Some of the typical examples of Lewis acid base reactions are below. Third statement is molecules in which the central atom has available d orbitals and may acquire more than 8 electrons. Compounds such as AlCl3, SiF4, SnCl4, SbF5, SO3 are Lewis acids, whereas the central atom can expand its valence shell. Fourth statement is molecules with a multiple bond between atoms of dissimilar electronegativities. Carbon dioxide represents an interesting example of a double bond between the carbon and the more electronegative oxygen atom. Oxygen, being more electronegative, has a tendency to attract the said pair of electron more towards CO2. As a result, it acquires positive charge on the carbon atom and becomes electron deficient and attached with the oxygen of the hydroxide ion. Similarly, sulfur trioxide acts as an Lewis acid towards water. Lewis bases According to this concept, Lewis bases may be classified as one of the following type of substance. First statement is negatively charged substance, anionic species. All the negative charged species are Lewis bases because they are rich of electrons and have a strong tendency to donate electron pairs. The greater the charger density of the anion and the stronger is the base. Second statement is neutral molecules with one or more than one unsaid pair of electrons. Molecules with unsaid pair of electrons act as an Lewis bases. For example, NH3 plus H2O, R2O and R2CO act as electron donors. Third statement is alkenes and alkynes with multiple bonds also form coordinate bonds with metal ions. Organometallic compounds, acid base reactions according to Lewis concept. Some of the typical acid base reactions involving in the formation of the coordinate bond between a Lewis acid and a Lewis base are summarized below. It is important to note that an empty orbital is being created on the sulfur atom by moving a pair of electrons from the double bond onto the oxygen atom. Combination of cupric ion with ammonia. Unswitch concept is very useful as it is classify all examples of acid and bases together. However, it is too general. This is because it considered even the oxidation reduction reactions as acid base reactions. Solvent system concept. The solvent system concept of acids and bases was postulated by Cady Ashley in 1928. It is an extension to the Lowry-Bronsted concept and it is applicable to both protonic as well as non-protonic solvents. According to this concept, an acid is a substance which either by direct dissociation or by the interaction with the solvent gives the anionic characteristics of the solvents. The characteristics cations and anions of the solvent are the ions produced during the autoionization. The prefix auto means itself. To illustrate this concept, let us consider the autoionization of some protonic and non-protonic solvents. Similarly to Arrhenius concept, neutralization reaction may be represented as a combination of cationic characteristics of the solvent with the anionic characteristics of the solvent to form the solvent's molecules. It is important to note that neutralization according to solvent system concept is the reverse of autoionization reaction. Types of solvents. Solvents are classified in a number of ways on the basis of their physical and chemical properties. Broadly, there are three ways in which solvents can be classified. First way is protonic and aprotic solvents. Solvents which contain hydrogen and can lose hydrogen in the form of proton are called protonic solvents. Common example of protonic solvents are H2O, NH3, H2S, HF, etc. Solvents from which hydrogen cannot be obtained in the form of proton are called aprotic solvents. For example, are CH3, CN, 6 h 6 etc. Solvents like N2O4, SO4, SO2 and CCl4, carbon tetrachloride are also called aprotic solvents. Second statement is acidic, basic and amphiprotic solvents. Solvents which have a strong tendency to give protons are called acidic solvents. Common acidic solvents are H2SO4, HF, CH3COO, etc. Solvents which have a strong affinity for protons are called basic solvents. Basic solvents are ammonia, hydrogen, pyridine. Solvents which display both acidic and basic properties are called amphiprotic solvents. For example of amphiprotic solvents are water, methyl, alcohol, etc. So third statement is OA. So our third statement is ionizing and non-ionizing solvents. Solvents which undergo self or auto-ionization are called ionization solvents. Typical examples of ionizing solvents are water, ammonia, hydrogen fluoride, sulfur dioxide, etc. Solvents which do not ionize are called non-ionizing solvents. Typical example of non-ionizing solvents are benzene, carbon tetrachloride, etc. Such solvents are non-polar and have low dielectric constant. So our inorganic chapter is complete.